Good morning, viewer. Welcome to our FTP English version. Viewers, cells. Cells convert mechanical forces into signals that influence physiological processes such as exercise, strengthening bones. So, a research team at Washington University in St. Louis and Tsinghua University in Beijing have discovered that biological tissues can also undergo dramatic phase transition or collective shifts where wound healing cells can switch from disorder healthy states to highly coordinated disease states like when water suddenly freezes into ice. This discovery, published October 3, 2025 in Proceedings of the National Academy of Sciences, reveals why prebiotic diseases often progress in switch-like jumps rather than gradually, and points to new therapeutic strategies that target the physical properties of tissue rather than just cellular biochemistry. The team used computational modeling to uncover the mechanical tipping point that determines whether cells can collectively coordinate to spread a disease called fibrosis, an excessive scarring that underlies failure of nearly any organ, and especially in diseases of the liver, lungs, kidneys, and heart. What we have shown is that this is not a gradual process, explained Guy M. Janine, co-senior author, and Harvard, and Kathleen Ford, professor of mechanical engineering in the McCalvey School of Engineering at WashU. There is a slow transition point when cells are within a critical spacing that depends on the way their matrix deforms. They can talk to each other mechanically through the matrix. Above it, they are effectively isolated, and below it, they interact strongly with one another. This on-off switch behavior is what we see in fibrosis progression, periods of stability followed by rapid scarring. Phase transitions are familiar in physics. Water freezes to ice at 0 degrees Celsius temperature, and iron becomes ferromagnetic below 770 degrees Celsius. The new research demonstrates that living tissues show similar behavior. When cells are spaced far apart in a tissue, they act independently, but when cell density crosses a critical threshold, a few hundred micrometers apart, they begin communicating mechanically and acting in concert, dramatically compacting and stiffening the tissue. The research shows why these phase transitions occurs. Fibrous networks like collagen enable long-range mechanical communication in a way that uniform elastic materials cannot. If you embedded cells in rubber, they could barely sense their neighbors even if they were close together, said Jiang Gujun Peng, first author and Sumu scholar at the Tsinghua University. But collagen fibers can be recruited and aligned by cells forces, creating stiffened tension bands that act as mechanical communications highways, transmitting signals over much longer distances. Then the exclusive report.